Hello, good morning everybody, or good morning, or good afternoon, or even good evening, depending on where you are in the world. We have folks from a number of different countries joining us today, and I just wanted to welcome you to another one of SonTek webinar series. Today we're going to be talking about the SonTek RiverSurveyor S5 system. I know we felt the S5 had long been hiding under the shadow of its bigger brother or bigger cousin, the RiverSurveyor M9. So we wanted to make sure that it wasn't left out of the family. So today, again, just wanted to present or introduce your presenters. Here on the left is myself, David Velasco. I'm SonTek's product line manager, and I'm being joined today by our hydrology product manager, Mr. Chris Evans. Chris?
Hi, this is Chris, and to begin again, I want to welcome everyone to the webinar. This is one of a series of webinars, all of which can be downloaded from our webpage if you've missed them. And today we will be talking about the SonTek RiverSurveyor S5.
Okay, great. Thanks, Chris. And to just begin here with a brief overview of what we will be talking to you about today, obviously we're going to introduce the RiverSurveyor system. We're going to talk about the S5 in particular, spend just a slide or two on the differences between the S5 and the M9. Then we're going to talk about a pretty interesting application from some folks using the RiverSurveyor S5 system to measure discharge in a very unique condition over in Greenland. I think you really appreciate certainly the photos we'll be showing here. And then we're going to just wrap up. And as a reminder, we are, like Chris said, we're recording this webinar. It will be made available to you for offline viewing later on. We're also going to have a question and answer time at the end of the presentation. So make sure to type in your questions via the chat. We have someone here who will be jotting down those for us, and at the end we will address as many of those questions as possible. And the ones that we don't have time to, we will answer in email formats to all of the participants at the end. So now as we move forward, first we just need to acknowledge that we have quite a diverse audience today. We have many participants who are experts on the RiverSurveyor system, both the M9 and the S5, as well as other move and boat discharge measurement systems out there. We also have a large number of our participants today with little or no experience in performing discharge measurements with an acoustic Doppler system. So in order to get everyone on the same page, we first need to spend some time just bringing everyone up to speed on the RiverSurveyor system, make sure we're all on the same page here. We understand that this, for some of you guys, this might be just review, while it could be new material for others of you. So just bear with us as we go through this for everyone's benefits. Who knows? Maybe even the experts might learn a thing or two. So this image here gives a very good overview as far as what the RiverSurveyor system is. Basically, we have an acoustic Doppler profiler that sends acoustic pulses that propagate through the water column. As these propagate through the water column, they're measuring the velocity, which is indicated here by the colors. The darker the reds, the faster the water, and the cooler the colors, the blues and the greens, the slower the water speed. So the system is mounted on some form of a floating platform. Here is, in this case, is the SonTek original hydroboard platform, now replaced by the hydroboard 2, which we will present later. And as that system is moved from one side of the stream all the way over to the other side, it's profiling this velocity. We're measuring depth as we go along. And once we combine that with the actual velocity, we're able then to compute your discharge. We have some optional devices here just illustrated, just for illustration purposes here. For example, a GPS system can be used as well to track the movement of the boat. And even though this image here shows it on a fairly small canal, this system can be used in manned boat applications as well, and it's not just limited to a hydroboard like it's shown in the picture here. If you guys remember, a few years ago we did a webinar showing this exact same system used on the Amazon, and you can download that webinar off of our website, for example, for you to see. So the exact same system with the same configuration can be used in a small channel like this or in a river as large as the Amazon. So that's just a brief overview of what the RiverSurveyor is. Again, it's a system that offers a number of neat features for measurement of discharge. And I just wanted to pass on now over to Chris Evans, a hydrology product manager, and he will discuss some of these particular features of the RiverSurveyor system as a whole.
Okay, thanks, Dave. For me, one of the most frustrating things working in the field is having to repeat your work. Not only adds cost to your measurements, it also doubles your time. This happens all too often when you lose communication in the field. One of the things that the RiverSurveyor system does is it records data simultaneously on the instrument and on your computer. So what this means is that if you lose your communication with the profiler, the data continues to be stored on the instrument. Another feature of the RiverSurveyor system is Smart Pulse. And what Smart Pulse does is it uses an adaptive mix of pulse coherent, pulse incoherent, and broadband. This allows the RiverSurveyor to adapt to the conditions by switching between the different pulse technologies and adjusting the cell size as needed. And because of that, it can handle practically any type of flow condition. The RiverSurveyor system configures itself automatically. The cell size, the number of cells, the blanking distance are all automatically configured. And Smart Pulse is automated as well. What this means is you don't need to do an initial exploratory pass to determine the flow conditions and the depth prior to the measurement, or have to set your mode for the measurement. Integrated echosounder is built into the RiverSurveyor. This provides a direct vertical measurement of the bottom. In addition, there's a 4-beam depth profiling and different locations across the section. This may not always give the best representation of the cross-section, but we do use it as a QA to our vertical beam. Okay, so what is the S5? What does the S5 do? You know, the S5 can profile from a depth of 0.6 to 5 meters. It can profile in velocities up to plus or minus 20 meters per second. And within this velocity range, the S5 has an accuracy of plus or minus 0.25% of the measured velocity. And the S5 can provide cells up to 128, ranging from 0.02 to 0.5 meters. The S5 uses 4 3 megahertz transducers, and the vertical beam is a 1 megahertz. When using the bottom track as a reference, the S5 can calculate discharge down to 5 meters. And when using our RTK GPS system, the S5 can provide discharge down to 15 meters. And all discharge calculations are done internally. The vertical beam, right here, in the RiverSurveyor system is used as our primary depth reference. And why is this important? This is an example of a measurement done with the RiverSurveyor system, and this is the 4-beam averaging. And you can see using the 4-beam average, you get a real nice smooth bottom profile here, averaging your depths. Using our vertical beam at the same cross section, the RiverSurveyor is able to detect sedimentation across that profile. And as you can see, the beams are aligned going across, but the forebeam has averaged out what the vertical beam is seeing along the bottom.
Yeah, Chris, I just wanted to add for some of the benefit of the viewers here. This is on a canal that is a trapezoidal in shape, and if you were to look at the green line here, which is the representative of the average of the vertical of the four slanted beams, you're going to see that trapezoidal shape kind of gets lost, certainly here along the edge. And that's one of the the key differences here. We're certainly this year, as we're highlighting the S5 systems in this webinar, we are showing some more shallow water type of data, but we definitely can have many other examples where of very drastic changes in the bottom that are not captured if you're just averaging four beams together. Because you have to remember, right, for all of the folks that are new to this application, if you're averaging these four beams, these beams are going to be hitting the bottom at different locations. And if you have a bottom shape that is very dynamic and could have vertical walls or big boulders or other features, you're basically going to be smoothing these out and not be able to really capture them. Whereas here, the trapezoidal shape of the canal is very clearly seen when we are using just the vertical beam only. So yeah, Chris, another great example here of the two methods that we can use for detecting the bottom and then coming out with a more accurate discharge.
Another example of the RiverSurveyor is the change in frequencies here using the smart pulse. As you can see, we're going across our cross-section here, and the frequency shifts, and then it shifts again for your edge. And this can be due to turbulence of some kind of a disturbance in the cross-section, but the RiverSurveyor is smart enough to know it needs to change its frequency to be able to capture the discharge that's in that part of the cross-section. Here's another example of some data that's been collected by the S5. As you can see, it's able to pick up cells and calculate discharge in water as shallow as 0.24 meters, and we're collecting velocities down to less than 0.03 meters per second, if you look at the scale here.
Yeah, this is, again, another, Chris, great example. If you look on the left side there, so depending on the resolution of your computer, you might be able to see there for some of the participants the number of cells that we have. And we actually have, on that very first sample there, we have 5 cells. We're able to build a profile of 5 cells in a total water depth there of about 24 centimeters, which is pretty impressive there. And it's not only the number of cells, so a fairly high spatial resolution, but you got to remember that these are being measured with post-coherent system, which is providing us with superb accuracy as far as velocity measurement is concerned.
And again, if you look over here towards the right edge of water, you can see this transition where the cells nearly double or are in half compared to what we're doing out here. Because again, the smart pulse has identified a spot where it can start collecting data in smaller cells. And so it's automatically transitioned between the two here. Here's an example of the discharge output summary from this measurement. And from those 4 passes, you can see that the mean Q is 0.018 CFS, and then within that, the coefficient of variability is 0.035. For 4 measurements in 0.018 discharge, that's pretty impressive.
That's very good repeatability. Yep.
So evaluating the decay of your acoustic beam can be important. Signal to ratio is a measurement of the strength of the acoustic beam in the water column, and the less particulate that you have in your water column, the weaker the signal is going to be. And ideally, each beam should be returning about the same strength coming back, and then, as expected, as you get near the bottom, the SNR is going to increase dramatically, and that's what you're going to see here. And so when you go back and you evaluate your SNR, you're going to know that all your beams are functioning, returning the same strength, and they're both seeing the bottom, or starting to detect the bottom, right about the same spot. So Dave, you want to talk a little bit about the S5 versus the M9?
Yeah, absolutely, Chris. Just want to kind of go back a little bit on when we're just touching base on the signal to noise ratio that Chris mentioned, because that will be important as well as we come towards the second half here of our presentation when we talk about this data from Greenland, which I'm sure everyone is excited to talk about. And just go back here, the slide. We are looking at something here that, again, gives us a lot of information as far as to how the system operates and how the water is. And, one of the issues that certainly the researchers who we're going to talk about in a bit about Greenland had a concern at the beginning is these streams there are very devoid of sediment. Is the S5 capable of measuring something that is going to have very little particulate matter in the water column? The water is very clear. I won't spoil the fun for you guys, but so we'll find out how that turns out at the end. But understanding what this graph means can be pretty important to analyzing the quality of the data that you have. As Chris mentioned, you want to make sure the beams are closely together. You want to make sure that you have a nice strong return off of your bottom, which is that spike there as the system approaches the bottom. The shape of that graph can tell you, like I said, a lot about the water, can tell a lot about the system as well. So let's just keep that in mind for now as we approach the description here. We're going to be talking about the Greenland data, because it's definitely going to come into play later on. But again, just switching gears a little bit, so we talked a little bit about the RiverSurveyor as a whole. We talked about the S5 and some of the features of the S5. But a lot of users out there are familiar with the M9, so they might be interested in knowing how does it really compare with between the M9 and the S5. Here we see on the photograph here on the right the S5 system mounted on our new hydroboard, the Sontex Hydroboard 2, which is large, much more stable platform than the original hydroboard. As you can see, just jumping here to the third bullet, physical size. The size of the head for the M9, the S5 is significantly smaller, narrower in diameter than the M9. We have less number of beams, so that allows for that head to be smaller. And in practical terms, what that means is lower flow disturbance around the head of the system. Go through that first bullet there, frequencies. The M9, as a lot of people know, operates in 3 frequencies, versus the S5 operates in 2 frequencies. And the reason for that is that we're able to have the large dynamic range that the system needs to properly operate with just that single frequency on the S5. We also have the number of beams is also different, whereas the M9, as the name suggests, we have 9 beams total, versus the S5 we have 5. There are 4 slanted beams and 1 vertical beam that's used for the echosounder. Like I mentioned, the size is significantly smaller on the S5 than it is on the M9. The range is also, the profiling range, that is, both for the vertical beam as well as the water velocity beams is different. Now, is shallower for the S5 than it is for the M9. But what all of this really comes down to is certainly on the end user is pricing. So it's something that a lot of users, they don't, they're not going to be operating in really shallow, in really deep streams. So what they do is, okay, well, if I'm not going to be operating in the deeper streams, I may not need a system like the M9. I might be able to do with a system like the S5, which is a more affordable system. So again, it really comes down to the conditions that the system's operating in. And Sontec has a wide distribution or a wide network of distributors and sales representatives in all parts of the world, and they can certainly guide you through identifying the proper system for your application. So again, the S5 operates in 2 frequencies. The vertical beam is at 1 megahertz, and the slanted beams operate at 3 megahertz. Another one of the not necessarily a difference, but one thing that is common between the S5 and the M9, and as we have illustrated here, is some of the accessories. All of the accessories that are available with the M9 are also available on the S5. So all of the GPS system is available, whether it's differential or RTK. The telemetry system available on both of the systems as well. And here illustrated is the hydro board used in action, which again the hydro board, here's the hydro board 2 system that we Sontec offers, and that system is available for both S5 and the M9 systems as well.
And Dave, if I could add that the new hydro board is designed for high velocities, and Mr. Arias has had great success with this down in Peru. And part of the design of this is when the nose goes down, there's a tension system on it that allows the board to rotate and pop up to the surface rather than go all the way down to the bottom. And we've been having great success with this board in those conditions.
Right, and from the image here, you can see, this is a case where the system was used off of, a tethered application off of a bridge. It was not, it did not use a counterweight on the line, as you can see. So the line is going directly from the bridge down to the system. So even in this condition, you can see, the system is fairly stable. It's fairly leveled. The hydro board itself is, has a curvature to it. So even though the bow might be coming up, the system itself is at a shallower angle than that. So again, another great example here of a mountain and stream type of operation using the RiverSurveyor S5 with the hydro board 2. So, we wanted, to not spend too much time on the technical aspects of the system. We just wanted to give you guys a brief, overview of it. But here is the part of the presentation where I think most people were most interested to watch, and that, using the S5 on ice. There's Disney on ice, and then there's the S5 on ice now. So the just wanted to describe this and give you guys a introduction, and then we'll dive into that part of the presentation. But basically, the goal here was or the topic is the mapping of the superglacial streams in lakes in the Greenland ice sheet using the RiverSurveyor S5 system. I think this is a very unique application and really highlights the strength of the S5 system in this very demanding and actually even dangerous environment, which is the superglacial streams on the Greenland ice sheet. So as a way of introduction, on behalf of myself and Chris Evans here, and everyone here at Sontec really, I'd just like to acknowledge here the true heroes of the story, and this is Dr. Carl Leglater and Brandon Overstreet, both from the University of Wyoming. And I just wanted to, to say thanks for them for allowing us to really tell their story. Brandon and Dr. Leglater were responsible for deploying the RiverSurveyor S5 system in collecting the data that we're going to show to you guys here in just a little bit. We also like to recognize, all the others without whose help really wouldn't have made this possible. Namely Dr. Lawrence Smith over at UCLA, who is the principal investigator on this NASA-funded project to study the Greenland ice sheet, as well as his co-PI and the program manager as well, Thomas Wagner. We also wanted to make sure to take the time to recognize all the efforts of Chip Rollins at Streamcraft. He was responsible for designing the pulling mechanism that you're going to see later in this presentation, and that really enabled the users here to safely and securely move the hydroboard with the S5 system from one side of the stream to another. And as you see in the pictures in a little bit, these are certainly very difficult conditions to operate in, and without the ability to properly move the system from located from one side of the stream to the other, it certainly wouldn't have the nice high-quality data that they were able to collect. And of course, last but not least, we definitely wanted to acknowledge and recognize all of the field and the logistical staff that were involved in this project, and wanted to say thanks to everyone over there. As you can see on the background here of the photo, this is one of these super glacial streams. As you can see, the very light, the water is basically transparent here. It's almost devoid of sediment. Just wanted to see here the general layout of the land. Obviously, no trees around here, no dirt or anything. This is nothing but ice. Everywhere, everything you see in the picture here is nothing but ice and water. So definitely, a very unique condition over here as well. So again, just give you an overview of the project and the objectives. As I mentioned earlier, this is a NASA-funded cryosphere project, and it's really seeking to achieve three main goals. First is to understand the form and the process and the evolution of superglacial bodies of water, whether they're moving or not, so either lakes or streams. The second overarching scientific goal of this project was to quantify the importance for the different paths of this great volume of water melting from the ice sheet. In this case here in Greenland, it certainly can be applied in other locations as well. In third, is really to attempt to estimate how much of this water is either staying on the ice sheet and how much is escaping it. So in summary, we'll come up with the budget of the water and the ice, and basically how much and where all of this mass is. And actually, just as a quick side note, certainly, the PIs and the other folks involved in this project maintain, some of the records online as well, and you should be able to find out some more information on their respective web pages as well online. But again, here, just to talk a little bit more about these streams and the conditions that the researchers are facing, and show some of these, just amazing photographs here. The superglacial streams are those bodies of water. They're basically moving water that flow on top of a glacier or another ice sheet. And they're formed by the melting of the glacial ice, and they can get quite large here. They're very dynamic, as you can imagine. In this particular study, there were streams of up to about 30 meters in width, and depths exceeding 2 meters were also measured. In some of the locations, the velocity was slow, but in others certainly was fairly fast. Here in some examples exceeding about 3 meters per second, which is about 10 feet per second. So again, very challenging conditions to be measured with an acoustic system. Just looking at the the extreme behavior that some of these super glacial streams present. Here on the top left image, you can see how a lot of these streams, they going through this, they can go through this abrupt transition from these fairly broad, or let's say the relatively broad streams into these deeply incised canyons. As you can see a transition here going from that, and all of a sudden there's a hydraulic jump, and it just goes right down through these canyons, these shallow canyons over here. So again, it comes up with a very different hydraulic condition, which adds to the challenge of measuring these streams and really be able to quantify them. And even the more tame of the streams here, in this case here shown in this bottom photograph, can all of a sudden just be flowing on top of the ice and just all of a sudden just disappear. Here's a stream, and we're showing a better image here in a couple photographs from now. But here you can see how one of these streams simply flowing on top of the ice and just disappears into a crevasse. Basically, the water finds a little crack on the ice, and once it starts flowing, that ice, that crack starts growing, forming a crevasse, and the water all of a sudden just gets sucked in. It's just as if you were pulled a plug from a river, and all of the water just flows down. Now here, the ice thickness here, I'm not 100% certain, but certainly in excess of probably a couple kilometers of ice that you have. How far into the Greenland ice sheet they were. So this water now is just cascading down this ice, and is all the way until it hits the bedrock or whatever sediment or substrate that's below the ice here. Again, very challenging conditions and dangers as well. Not to mention, of course, all of that you see here is ice, so the water temperatures that you're dealing with are just barely above freezing. Here's another great photograph here showing the RiverSurveyor S5 system in action. And we'll talk a little bit more about the measurement setup in a little bit. But you can see here the pulley system that was designed. You can see the safety line, the operators, one on one bank and the other on the other bank. You can see how the water here is pretty clear. That's the blue coloration comes in, from the fact that the water is it's cold and is clear and is surrounded by ice, on all sides. One thing, just as a side note, you see some of the darker images here on the ice. So there's definitely sediment, other aerosols that have been deposited on top of the ice. So there's some particles in the water, although it's nearly devoid of sediment. So you can see, for example, here a crack on the ice, some crevasse, starting to form over here, and one of the objectives of the study is to try to determine or try to understand these dynamics, and is this going to be, is this stream eventually going to be swallowed up by this crevasse, for example, here? Some of the things they're trying to determine. You can see certainly, the dynamic surface conditions that we see here, in the photograph. You have some standing waves, water just ripping through these channels, and so needless to say, dynamic, pretty challenging conditions here. On the center of the photograph, you see the hydro board, the original hydro board, not the hydro board 2, but the original hydro board from Sontec, the S5 system in the center of the board with the GPS. All of the data that they had here was referenced to RTK, Sontec RTK GPS system for boat positioning. As you can imagine, there are no roads anywhere here, and there's no way to get to and from the site other than helicopter. As a matter of fact, just to get from one side of the stream to the other, you need a helicopter to get. So, not something that you want to, not your typical stream. You can also see some of the dynamics of the environment here. You see a fairly, fairly okay flowing water here, not very fast, but then just jumping into to potentially coming into a crevasse or merging in with another stream over here. But again, very dynamic conditions to measure in difficult conditions where the S5 certainly excelled at. So again, everywhere that you have to go here, you got to go by helicopter, which adds cost, of course, and adds complications to the measurement. And definitely not a location where you want system to be failing on you and to be not working properly. Like Chris mentioned early in the presentation, last thing that you want to have when you're out this far away from civilization is something that is not going to be working correctly. Here's another great photograph of basically what we're showing here. This is an aerial photo taken from the helicopter. You can see the shadow of the helicopter over here. So here is a small, I would say probably about 20 meters or so wide, a stream that comes out through the top of the ice. And you can see at one point it was flowing down this channel over here. But a crevasse has developed, through a crack here in the ice, and the force of the water has slowly chipped away this crevasse, enlarging it, and now it's big enough that the entire river, it just gets sucked into this waterfall through the ice and dropping, several hundreds, if not thousands of meters down all the way down to the bedrock. So again, another very powerful image to illustrate not just the complexity of these channels, but also the danger that it can be measuring something. Definitely not, the type of location you want to fall in the water over here. Because if you fall in here and you're down this crevasse, well, let's just say that you wouldn't be around to watch another webinar. So, definitely one thing you want to keep, keep in mind here as we go through these slides. So here, let's talk. I know about the actual equipment used. Talked about the helicopter already. Just to get the researchers out to the site and from one side of the stream to the other. This is the Streamcraft cableway system that we're talking about that was developed. But basically, it is a system that, and I have a few other photographs in a little bit later, but that's anchored on the ice. And then that is used to pulley the system from one side of the stream to the other in a very controlled and very nice manner. Here you have the RiverSurveyor S5 system with your RTK GPS system. The base station for it is just outside of the photograph range here. You have your power communications module with your battery, which supply power to the system and also houses the GPS and the data telemetry system. So the system just sends that data out over to the user on the bank. So talk a little bit about the measurement procedures here that were used. Basically, like I mentioned, on one side, the cableway was secured to the stream bank using the ice screws, and then with these straps here to keep it nice and straight and taut. Then the helicopter was used to fly another operator to the other side of the stream, and the same cableway system installed on the opposite bank, and the system was anchored. Then basically a line with a weight on it is thrown across the stream just to get the initial line out. That line is pulled then across, tied into the rest of the system here. And what you see is that this top pulley system here is used to keep the whole line stretched and taut around the, from one bank to the other, whereas the actual M9 itself that is attached to this bottom line, and these reels are used to push or pull the system from one side of the stream to the other. So pretty ingenious system here that was used, works pretty well on, when you have, nice access to the banks like you have here in this particular setup. Switching over here just to continue to talk a little bit more about the measurement procedures. The cable was, obviously, like I mentioned, was tensioned using the hand crank, and then the S5 was attached to that cable. The line attached to the reels on each bank was, again, also attached to the S5. And the way that the system was used was that it was operated with using the smartphone. So the data is being telemetry in real time from the S5 system all the way to the operator on the bank, where he can actually collect the data, without obviously not having to get in the water or have to lug a big laptop around with him. So here again, just getting over to the edge of the stream here to drop the S5 into the water.
And Dave, this is another example of the importance of the data redundancy with the remote communication and the data being stored on the system itself. And so in this instance, we're talking about expense. It's not going to be cheap if you end up spending double the time out here with the system. And so if you were to lose communication here, again, you'd be able to retrieve the data from the system itself.
Absolutely, and that's certainly a great advantage of the RiverSurveyor S5 system, because like Chris said, you certainly don't want to have to go back to the office, when you're all the way out here. You want to go out to the site, get your data, and then come back. So let's talk a little bit here about the data from this setup that we have over here. We have, I wanted to start this slide. I had to kind of slide a little bit backwards here, but wanted to talk about. This is just a summary of the data. I have, I didn't want to show all of the data here that was collected, but just to show you, this top graph here. These are just used by sample number here, and it's roughly about. This represents something in the order of about 20 meters across, or so, about 15 to 20 meters across. And obviously, you have depth here from all the way to the surface. This particular case here was not quite 2 meters deep. The top part of the top graph here is your speed, the water speed in meters per second based on this scale. This is the direction, and based again also on degrees here. Because it is straddling the 0 to 360 boundary, you have the sharp contrast in color here, although that's certainly not indicative of a significant direction change. It's just that they're straddling the 0 to 360 heading here. And lastly, this is the error, the standard error of the measurement, and you can see, basically we're talking about significantly lower than what your measurement is. So very high accuracy and high resolution velocity data over here. But again, you can see how the streams are can be fairly dynamic. You get some spots here with some pretty slow moving water towards the surface, where things are deeper here, followed by some locations with some fairly fast water. So it's definitely a significant transition or shear right here in the middle, somewhat closer to the bank. So it goes to illustrate some of the dynamic conditions that some of these sites can observe. Go back here. We're talking about the SNR data, that signal to noise ratio, and this is what is shown here on the screen for that exact same transect that we just shown on the previous slide. But basically, if you remember, Chris talking about the SNR profile and how that is important to, as a way to understand your data. And what you have over here basically is a map or a color map contour, that is, of your SNR for your beam number 1, which is the top graph, and then beam number 2, 3, and 4. This is the scale here in decibels for SNR. You see your sharp contrast here where the bottom is, okay? And you see how here in the deeper area of the stream, we're very close to almost 0 decibels of SNR. But fortunately, the S5, is certainly capable of measuring valid velocity data down to very low scattering conditions, such as these streams over here. Even though we're really approaching the limit of the system here, we're still capable of measuring valid velocity data, even on these areas here where the where your SNR or the strength of that acoustic pulse is really diminishing because the streams have poor scattering conditions. I'll just go back here to that. So here, what I wanted to, another slide that we wanted to show to you guys here. This is from one of the transects. You can see here reference to GPS data. You can see how the grid here is about 2 meters. So each of these square here is about 2 meters in diameter. So here we're looking about 10, maybe 15 meters or so in width. Actually, more like 20 meters in width. You can see how the nice, smooth, straight method or way of moving the boat from one side of the stream all the way to the other with the Streamcraft cableway system that was developed. You can see how the depth, these vectors represent depth average velocity vectors, which they're fairly well aligned. So this here in a particular location is a fairly well behaved part of the stream. Although you start seeing some impacts here of that more dynamic condition here towards the left bank. And here on the bottom side of the screen, you see the three-dimensional profile of the speed. So you have your bottom over here. You have each one of these blocks is the location where a three-dimensional velocity measurement has been made. Here you have left edge of water, right edge of water. And you can see how the velocities here, just judged by the color scale here, are coming up to about a meter, maybe a meter and 20 centimeters per second here. So a typical stream, typical conditions over here. Another data, or again, this from the same transect, but another set of data that in this, all of these graphs here are coming directly out of the RiverSurveyor software, or the previous slide and this slide, I should say. So these are directly out of the RiverSurveyor software, and they make the analysis of the data very, very straightforward. So again, at the top graph here, you're looking at the boat speed, which is this blue line here. You can see how they were able to successfully maintain the boat speed, very consistent using that pulley system. These bars represent the ratio of the boat speed to the water speed. So they were at about half of moving the boat at about half of the water speed, which is again great boat displacement conditions over there that they were able to maintain, even though the conditions at the site were very dynamic. Again, this is the heading. The second graph is the heading data from the actual compass inside of the S5. And what you can see here is how they were able to, again, maintain the heading for the boat, very consistent, very aligned with it, which again is a typical of a tethered application. But you can see just the stability of the board in this condition. One thing that I wanted to show, this last graph, this is something that the RiverSurveyor software provides, is the speed in the last cell. So this is the bottommost cell from the system, and in other words, it's the one closest to the bottom or closest to the ice, I should say. This here is it just shows how dynamic the environment really is. You have a condition here where you have these velocities are just going all over the place on the bottom of this channel because of the bottom is so the hydraulic conditions over there are so diverse. One thing that like Chris mentioned, we have both smart posts and the automatic switching of cell size and frequencies and number of cells. And this graph here shows that we started off with a particular type of measurement over here in your smart post. We switched over to incoherent because of the velocities we're picking up. When velocities are slowing down too, switched back automatically over to smart post. So the system not only tells you when it's doing this, but again, it's able to do this on the fly automatically. And lastly, I just wanted to show you, the tilt of the pitch and roll of the system over here on the bottom graph. And you can see how even in this challenging condition, they were able to maintain that vessel very well leveled and very smoothly across from one channel to, or from one side of the stream to the other. So again, just to wrap up here in conclusion, we're coming up here to about 10 minutes to the hour. I wanted to thank everyone for joining us in this webinar. We have a number of questions that are coming in already, and we're going to be trying to address these as much as possible here, and in the time given. But if we don't get to your questions, like I mentioned, we will certainly answer all of them via email later on. So just in conclusion here again, want to thank once again Brendan Overstreet and Dr. Carl Leglater from the University of Wyoming for allowing us to tell their story. This is really their story. This is really the data that they collected. And again, just these are really their conclusions. Which is great to get that really good positive feedback from a user in such a dynamic and in harsh condition. Again, they can show how the S5 delivered consistent measurements of discharge for streams ranging in all the way from about 4 up to about 20 cubic meters per second. Another point is that the S5 maintained really acceptable SNR in most streams in this study, even though they were ultra-pure meltwater that were nearly devoid of sediment. So again, another very challenging conditions. The S5, another conclusion that we can certainly draw is that the S5 certainly derived valid depth and velocity measurements, and this data is being coupled actually with, as part of the research that these researchers are doing, coupled with other satellite images to estimate the overall surface water flux on the Greenland ice sheet, which obviously is something that has strong repercussions for the climate change research. So just wanted to, on behalf of myself and Chris Evans, thank everyone for participating in this webinar. I hope that it was beneficial to everyone, and just wanted to again say thanks to everyone. And we're going to switch over now to our questions and answer time. And like I said, we have a number of questions here on the queue already. We'll try to get as many of them as possible. Apologize in advance if we can't get to them, and then but we'll be able to answer them in due course via email to all of the participants.
Yeah, and Dave, we have a few here that are related directly to the Greenland data that you've been showing.
Okay.
So I think we'll start off with those.
Okay. Give me a second here, everyone, while we read through these questions here and start picking out the one. Okay, there was a measurement or a question here concerning how some of the measurement profiles that were shown, the velocity appears to be shallower than the acoustic depth. And so how can this be accounted for in the flow measurement calculations? It's a great question and one that we get quite often. And basically, if you go through, let me see if I can go back through some, here is perfect slide here. For all acoustic Doppler measurement systems, there are several sections of the streams that are measured and others that are estimated. You have the surface layer here, which cannot be measured due to the transducer depth into the water, as well as the blanking distance of the system. Obviously, on the left and on the right edges, it cannot be measured because the boat can only get so close to the water edge. And then on the bottom as well, which this particular question is in reference to. So basically, this is the same for every single acoustic Doppler profiling system out there in the world. And what it's done is that the top, both the top and the bottom parts that are unmeasured are extrapolated based on either a user-defined extrapolation equation, basically a power law, 1/6 power law. The user can change that exponent, and there are different methods out there to estimate that. On the edges as well, the measurement is estimated based on the velocities close to the edge. And like I said, this is a system that was or not a system, but this is a series of calculations that is used throughout all of the for all of the acoustic Doppler systems out there in the world. Now, again, and just one last thing on this topic. This is a question that comes up quite a bit because people are looking at it and they look, oh, okay, well, what about these other areas here that are not measured? Well, if you considered, a mechanical current meter, which has been, sort of the tried and true method of measuring discharge, instantaneous discharge for well over 100 years, a mechanical current meter is actually only measuring about 0.0009% of an actual area of a particular stream. It is estimating well over 99.99% of a stream. Here on a typical stream, I don't have the data for this particular image here, but I would probably venture to saying that we're actually measuring about 60 to 70% and estimating the remaining 40 or 30% or so, which is sort of typical, rather than in a mechanical current meter where you're estimating well over 99% of the actual area. Here's another question that we have here is, there was I guess it's in reference to the slide. Let's see if we can go back there, the slide on the SNR profile. We're talking about measuring some SNR or below the bottom profile. So here, I believe the question is in reference to this over here. And this is another common question that we get, and this is just an artifact of the actual graphing of the software. There's no actual penetration of the acoustic pulse into the bottom. What we're seeing here is just an artifact. And if I were to have changed the scale on this particular graph here, we would have actually seen even more of that data, even though that's not real data right there. We're only looking at the velocity all the way up until the point where the system starts picking up the bottom.
There's a few questions here, Dave, that I think I could probably answer in one. They're all similar. The frequency of the vertical beam is 1 megahertz. We'd have a question on the frequency there. We've also have how fast can the boat move across a transect, and ideally you don't want to be moving faster than the velocity. So if you can maintain movement less than the velocity you're seeing, you're gonna get the optimal profile. See here.
Oh, okay. Here's another question where it's talking about the maximum river depth that the RiverSurveyor S5 can measure. There was also another question there that asking also about the M9, and so just to give you an answer to that. So the S5 system, when you are not using GPS, you can measure velocity down, valid velocity measure down to 5 meters, or I should say discharge computation can be done down to 5 meters. With the M9, that's down to 40 meters. When you are using a GPS or some other external track system for boat displacement, in other words, you don't have to rely on bottom tracking, then you can extend that range down to 15 meters for the S5 and down to 80 meters for the M9. So basically what you're talking about is that you're measuring up until that certain point with the velocity down to 5 meters in the case, and then you're extrapolating the rest. Because remember, the vertical beam for those systems do have the capability of picking up the bottom much lower or much farther below the system than the slanted beams can, which are the ones measuring the velocity. So again, in summary, without GPS, S5 can measure down to 5 meters and the M9 down to 40. With GPS, the S5 can measure discharge down to 15 meters and the M9 down to 80 meters. Let's take a look here at some other questions here. There's a question here about, so the question is, what happens when the boat encounters hard turbulence and jumps? Can signal get lost? Well, it depends on what the question means here as far as jump. Now, if it's in the case of a hydroboard and the system actually becomes airborne, let's say hits a wave and actually comes out of the water such that the transducers are decoupled or lose contact with the water, yeah, sure, for that particular second where that happens, you can, yes, lose signal. That does not mean that you're going to lose your measurement altogether. It just means for that 1 second sample, you're going to lose your signal. Now, as Chris mentioned, we have, between a smart pulse and the automatic configuration of the system, we're certainly able to deal with both the laminar flow as well as turbulent flow very well. And one of the slides that we had shown earlier shows just that particular transition. See if I can find it here. But again, we're shown here a more sort of well-behaved part of the stream here. Once the stream starts picking up velocity and turbulence, we're switching into a different method of measurement here that allows us to capture that data without really sacrificing the quality. Let's see here, some other questions. Okay, so there's a question here that's really comes down towards the the application of the system rather than the actual system itself. And the question is, does the transect have to be perpendicular to the river flow? And what is the tolerance, or how can one say that the measurement is not good or good based on the how perpendicular it is to the transect? Now, basically, the system can handle a variety of angles to the flow. In theory, it can handle almost any angle, or it can handle any angle to the flow. What starts becoming an issue is that as you have that section that is less and less perpendicular to your flow, you are no longer measuring discharge along one specific cross-section. If you were, for example, to exaggerate that and say that the transect is so angled to the flow that you start at the bank at one location and you're on the opposite bank, you're, let's say, 100 meters farther downstream, well, you're covering there a very wide range of the river lengthwise. So it's not really the same section. We can't really say, exactly at what angle it will become acceptable or not. And that's really up to, the user community and the different agencies out there who are responsible for delivering this data to the public, and they can, certainly draw up guidelines. Certainly here in the USGS, there are guidelines. Here in America, there are guidelines for what's acceptable or what not. But there will always depend on the condition. It will always depend on the setup of the system itself. But as a rule of thumb, the more perpendicular that you can make, the more realistic your data will be of the actual reality of the system here. Let me see if we can answer a couple more questions here. I know we're over the 1 hour mark, and I want to respect people's time here. There's a question here on the applications that I hope I can address, which is, what is the performance difference in glacier streams versus mountain streams? Again, a great question. I hope that I can address this, accurately. Basically, they certainly, both glacier streams and mountain streams are going to have, or can have, fast-moving water, very dynamic conditions, a lot of turbulence. I think one thing that the glacier streams are going to be different than the mountain streams is that the mountain streams, more often than not, are going to have a higher sediment concentration. Certainly, if you see some of the image that I had here of this image in Peru, this is a mountainous stream, and you can see similar surface conditions than you saw on the glacier, super glacial streams, but the sediment content here is significantly different. So perhaps I think that the setup of the vessel itself and how it's used is going to be very similar, but the results could be somewhat different. You're going to have certainly much more scatters. I think in this case of the superglacial streams, you're going to have one extremes of not having enough scatterers in the water, versus the other where you're going to have perhaps too much sediment in the water. So it's tough to say one way or another as far as performance, but certainly I think we've shown here that the S5 is capable of handling both of them.
And to add on to that, Dave, there's another question about the signal decay with the sediment load, and you're going to see the same decay. You're just going to see a shift in your decibels. The higher sediment you have, you'll see that shift, and that goes same as you go in less decibels, like we see with the glacier streams. So as far as the decay goes, you're going to see the same decay rate. What will happen is if you get too much sediment, you may not be getting that return signal, and so you won't be seeing the decay as we were seeing in the examples earlier.
Okay, let's see here if we can pull out one more question here. Again, we're coming up to our time over here. Let's see here. There's one last question here. I just want to make sure that we get it covered. And it's talking about explain the water track modes, and Sontec uses a mixture of post-coherent and post-incoherent in indirectly broadband as well to measure the water velocity. But the system is either going to, as far as the velocity the user sees it, it's either going to be post-coherent or post-incoherent. And what the system uses is an algorithm that looks at depth, it looks at the maximum velocity, it looks at the level of turbulence, and also is an adaptive algorithm in the sense that it's also looking at what the stream or what the river is doing up until that point, so that it can adjust itself and can pick the conditions more appropriate for each individual sample. So it's doing this calculation on every 1 second and trying to determine if what is the best method possible to measure. If it is post-incoherent, which is your traditional narrow band, it's going to use that. If it is post-coherent, it's going to do that as well, or instead of it's going to use that. So again, it's going to switch not just on this processing technique between post-coherent and incoherent, but it's also going to switch on frequency as well. So you can have, for example, you can be bottom tracking on 1 megahertz post-incoherent, but water tracking, meaning measuring velocity, with 3 megahertz post-coherent. So the system is, all of these methods are completely independent of each other. The frequencies are completely independent from each other, and are used to automatically on a second-by-second basis to determine the best possible data quality that you can get for that particular stream. So with that, we're going to wrap things up over here. We are again wanted to thank Brandon Overstreet, Dr. Carl Leglater, and all of the others that we acknowledged earlier for allowing us to tell their story. Wanted to thank all of the participants here for being so patient with us through this last hour here through this webinar. Again, we're going to address all of the other questions in a follow-up email to all the attendees, and the webinar is going to be posted on our website as well for you to watch.